All right, everyone. So next Tuesday, it looks like next Tuesday is the last lecture. So then we should, so I will try to finish lecture 10 today, which is talking about Z transform, a discretized version of Laplace. And then next Tuesday, we can have a review lecture. Right. So given lecture 9, given all the backgrounds of Laplace transform, Z transform is a discretized version of Laplace, can be understood as a discretized version. So remember, we introduced what happened? Something wrong. Okay. What happens before the present? Somehow my pen is not working. Below this. So we talked about the Fourier transform and the discretized version, still not working. For 2 slides. And then we introduced the DTFT, the discrete time Fourier transform, which works for discrete signals. And here we have the same story. We first introduced Laplace transform that generalizes the Fourier transform. And then in the lecture 10, we're going to talk about the discretized version called the Z transform, which generalizes the discrete time Fourier transform. So the definition of Z transform is very similar to the discrete time Fourier transform. Now here's the definition. Given a discrete time signal xn, the Z transform, which we denote as xz, is given by this summation with summing over xn times z to the power of -n. Now in the discrete time Fourier transform, we use z, we set z to be e to the power of j omega. Okay, that is the a very standard basic complex exponential. So that is the discrete time Fourier transform. And in the complex plane, this corresponds to a circle in the complex plane. Why? Because if you view this as a polar form, e to the power of j omega, okay, now it works. So e to the power of j omega, I'm using my hat. This one is a complex number that has a constant magnitude 1 with arbitrary phase. So if you draw this on a complex plane, it will correspond to a circle. All the complex numbers that has amplitude magnitude 1, they form a circle on the complex plane. So in that sense, the discrete time Fourier transform, the domain of the discrete time Fourier transform is actually corresponds to a circle, a unit circle on the complex 2D complex plane. Right, this is the real part of Z. and that's the imaginary part of Z. So the idea of Z transform is again very similar. Is to trying to extend the domain of DTFT to the entire 2D complex plane. And the way to do that is to add an amplitude magnitude variable R and allow the Z transform to be performed on the circles of arbitrary radius. And this once this R ranges from 0 to infinity, we can cover the entire 2D complex plane. So here in the Z transform, we replace the e to the power of j omega by R times e to the power of j omega. Now this is a standard polar form of complex number, so it can cover any arbitrary complex numbers over the 2D plane. However, if we set R equals to 1, which corresponds to the DTFT, then e to the power of j omega only covers the complex numbers circle. Okay, so in this sense, Z transform generalizes the DTFT. So if we consider Z to be e to the power of j omega only, which corresponds to this unit circle in the Z plane, then the Z transform simply becomes the discrete time Fourier transform. It's a special case. And on the other hand, more generally, in the general case, Z transform covers the entire complex plane. The domain covers the entire plane. And similar to the Laplace transform, Z transform can be understood as a type of DTFT. So in the sense that we write, let's plug in the form of Z. Let's plug in the polar form of Z into this definition. And then we have a real part, which is R to the power of -n. We can combine this part with the signal. And then the rest of the exponential part, we leave it there. So this can be understood as the DTFT of such a signal. Is the signal of interest xn scaled by another exponentially decreasing signal, right? So the basic idea is very similar to the Laplace transform. And then we also need to talk about, again, the most important concept, the region of convergence. So here the region of convergence is defined in the same way as the region of convergence of Laplace transform. It's basically considering all the z's, all the value of z, such that in this integration, in this summation, such that this summation will converge. So this is the definition of the region of convergence. And the sufficient condition for ensuring region of convergence is to make sure that this summation is absolutely integratable. Okay, now it works. Keep it. So the idea is this. Now looking at this definition, so summation of xn r to the power -n e -j omega n. Right. So in order for this is a summation of complex numbers, a series of complex numbers. So a sufficient condition is to make sure that it's an absolute It's an absolute summable criteria, which means that the summing up all the magnitude of the complex numbers, if this summation converges, then the original theory will converge. And by the basic property of complex number, we know that the magnitude of a product of multiple complex numbers, like all these, can be generally understood as complex numbers. A magnitude of a product of multiple complex numbers equals to the product of their individual magnitudes. So this gives us this reduces to the magnitude of the product of the first two terms, because for the last one, it is a complex number with magnitude 1. So we can ignore that part. So as long as this is absolutely summable, then we are guaranteed to have convergence. So that's why we have this criteria. Okay. And because r to the power of negative n is a positive number, so we can pull it out of the absolute value, right? This r is a magnitude of a standard complex number. So the range is from 0 to positive infinity. It's guaranteed to be non-negative. So basically, this is a sufficient condition for the region of convergence. And in particular, if the region of convergence happen to include the unit circle, because on the unit circle that we have DTFT. So if the ROC includes the unit circle, that means for this signal, we have the discrete time Fourier transform exists. So let's look at some examples of this Z transform and how to calculate this ROC. So again, let's look at this standard signal, alpha to the power of n, this exponential signal times, it should be un, okay, standard unit step signal. So this is a causal discrete time signal. Now, calculating the Z transform, we simply follow the definition. So this is the signal times Z to the power of negative n, taking the summation. And because of this un, we can combine it with the summation, so that we just need to start with 0 to infinity. Okay, and this alpha to the power of n and Z to the power of negative n, we can combine them together. So it's alpha divided by Z to the power of n. So this is a very standard infinite summation. So we can use this formula. We have introduced this before when we talk about discrete time transforms. So using this general formula for calculating the summation of infinite series, we can get this result. Okay, we can get this result. And in this result, the only term that is not determined is this term, alpha divided by Z to the power of infinity. This term may or may not diverge depending on the value inside the parentheses. So here we use a criterion. Here's a general criterion. A complex number inside can be viewed as a general complex number. Any complex number to the power of infinity converges. That means it has a finite value if and only if when its magnitude is less than 1. Okay, so this is similar to the case of real numbers. Therefore, the ROC is determined by the convergence of this term. And the convergence criterion is that the magnitude of this complex number must be strictly less than or equal to 1. Therefore, this gives us the ROC. right? So it's from this criterion alpha divided by z strictly less than 1, we can solve for z. And the solution is z. You can multiply by the magnitude of z on both sides. So z greater than alpha. So this describes a region of convergence for the variable z. Okay. So this is ROC. And within this ROC, this term converges. And in particular, we know it converges to 0 because it has a magnitude strictly less than 1, and we are raising it to the power of infinity. So it will diminish in the end. Therefore, the conclusion is that this is the ROC, and within this ROC, the Z transform simply becomes, we can ignore this term because it diminishes to 0. So it is simply 1 over 1 minus alpha times Z to the power of -1. So this is exactly the same as the Laplace transform. Well, in the Laplace transform, we also, instead of summation, we did some integration, and for some of the terms, it is raised to the power of infinity, and that may cause divergence. And what is special about Z transform is that if you look at the ROC, you will find the region of convergence, the ROC of Z transform is always looks like circle. So if you visualize this on a 2D plan, right? So the ROC is the magnitude of Z bigger than a number. Alpha should be given. Alpha is involved in this given signal. So the magnitude of alpha, it should correspond to a positive real number. Okay. So let's say this is alpha, the magnitude of alpha. Then the magnitude of Z bigger than magnitude of alpha corresponds to, draw a circle with the radius of magnitude of alpha, and then the outer region, the region outside this circle, gives the ROC. So in this region, all the complex numbers in this region has a magnitude bigger than alpha. Right? So we will see later that for Z transforms, the ROC is characterized by these circles. And this is a fundamental difference from the Laplace transform, where the ROC is characterized by vertical lines, either vertical strips or vertical left or vertical right half open planes. So here is always characterized by circles. And the second example is slightly different signals, negative alpha n to the power of n times u negative n minus 1. So you follow the same steps, compute the Z transform. So this is the definition. And then because of this u function, u signal, the summation actually starts from negative infinity and up to -1 because of this u function. And after that, so we combine alpha and Z together, and we do in order to make it more convenient, we do a change of variables, so the summation starts from 1 to infinity instead of negative infinity to -1. Okay. Do a simple change of variable, so we have a standard summation from 1 to infinity, and then alpha to the power of negative m times c to the power of m. And for this one, now this is a standard infinite summation. So you apply that general formula. You apply this formula. Okay. Once you do that, you can obtain this one. And again, there's one term that needs to be discussed. So in order for this term to converge, again, by the same criterion, we need this complex number. We need its magnitude to be strictly less than 1. So that gives us the region of convergence. But in this case, it's slightly different. When you solve this equation, inequality, we have z, the magnitude of z must be less than the magnitude of alpha. And within this ROC, this term will diminish to 0. So we can ignore that. So in the end, the Z transform simply becomes this one after simplification. So the conclusion is that this is the ROC, and within the ROC, the Z transform is given by this fraction number. So as you can see that in this case, for this signal, the ROC is inside this circle. Okay, it's the magnitude of Z less than strictly less than alpha. So it corresponds to area that inside this circle. And putting these two examples together, we can see that we have the same observation as what we have in the Laplace transform. So for different signals, we may have two different signals that have the same Z transform, but completely different ROCs. So again, when we talk about Z transform for discrete signals, the most important thing is the region of convergence. And these are the pairs of Z transforms that you can utilize to do the homework or to do the exam. So later we will use it to find out the inverse. And here's another signal, which is 1/3 to the power of n times sin times un. And for this one, we can view it as this signal, the 1/3 to the power of n times un modulated by the sine signal. And then this reminds us of the basic properties of the discrete time Fourier transform. So here the idea, we have done this many times, is to utilize the inverse Euler's formula to decompose the sine into the exponentials. So once we do that, decomposing the sine into the exponentials, and those exponentials can be combined with this term, the first term. So in the end, the xn can be equivalently written into this form. Okay, so the sine is decomposed into two exponentials, and then those exponentials can be combined with the first exponential. Okay, now we have two terms. If you look at each term, now this is a constant, so you can put it aside. And this is an exponential part, some complex number to the power of n times un, right? And for the second part is the same thing. It is another complex number to the power of n times un. Therefore, we can utilize the result in example 1 to quickly get the Z transform. Right? So here the alpha can be generally a complex number. So in the end, in ROC, we are talking. It is related to the magnitude of alpha. Therefore, use the example 1, directly use the example 1, we can get the Z transform of this one is simply given by this fraction number. So in this case, you set alpha to be this complex number. And the corresponding RLC is the magnitude of Z bigger than the magnitude of this complex number, right? According to the example one. And for the second one, again, you apply example one. So in this case, alpha becomes this complex number. So you get this Z transform, and the corresponding RLC is given by the magnitude of Z bigger than the amplitude, the magnitude of this complex number. And then, as we have discussed in the Laplace transform, in order to have a global convergence for both terms, the final region of convergence should be the intersection of these two. And if you look at these two RLCs, the first one on the right-hand side, we are looking at the magnitude of this complex number. Now, this is a complex number in a standard polar form. So by definition, the magnitude is simply 1/3. And for this one, it's the same thing. It is in a standard polar form. So the magnitude is 1/3. So in the end, these two RLCs are the same. So the overall RLC is simply magnitude bigger than 1/3. So it's the outer part of the circle with radius 1/3. And the RLC of Z transform has many basic properties. Like the first one, we have already observed that the RLC is always a ring type centered around the original point. And by the convergence criterion of RLC, because this criterion only involves the magnitude of Z, so this means that the RLC will only depend on the magnitude, not the phase. So that's why the RLC is always corresponds to a ring type. It's like a circle, either a circle or a ring. And similar to the Laplace transform, if the Z transform takes a rational form, right? If the Z transform is a fraction number, both the numerator and the denominator are polynomials in Z. If it takes a rational form, then the RLC should not contain any poles. Again, we can also define the poles of this rational Z transform. Now, if the signal is of finite duration, then we do not have any convergence issue because the signal only lasts over a finite duration of time. So the summation is guaranteed to converge. It will never diverge. In that case, the RLC is the entire Z plane. Okay, so these are the basic properties. And then the rest of the properties, RLC properties, are very similar to the RLC properties of Laplace transform. But the only difference is that here the RLC is of a ring type, a ring shape or a circle shape, whereas in the Laplace transform we have vertical RLCs. But the general idea is very similar. So if the signal is right-sided, then RLC extends outward in the Z plane. So like this example, the signal that we are looking at, it has a UN in it. If you go back to example one, it has a UN. So this signal is right-sided. And in the end, if you look at the RLC, it is outward this circle. Right, so it satisfies the first property. Right-sided signals has ROC that extends outward in the z-plane. And if the signal is left-sided, then the ROC extends inward in the z-plane. This one is the second example. Go back to the example 2. This signal is a left-sided signal because of this u negative n minus 1. And in the end, the ROC corresponds to the region inward this circle, right? So it extends inward this circle. And then if the signal is two-sided, then the ROC is the intersection of outward and between the outward and the inward. So that will gives us a ring in the z-plane. Right? But in the Laplace transform, if the signal is two-sided, that gives us a vertical strip in the z-plane. So the only difference is their shape. Laplace transform, we have vertical ROCs, and for the Z transform, we have ring-shaped ROCs. And here's an example of two-sided signal. Well, the xn is b to the power of the absolute value of n. Well, b is a given positive number. So again, we can decompose this two-sided signal into a right-sided signal plus a left-sided signal, so that we can get rid of the absolute value of n in this exponential. And then for each of each of these signal, we can apply example 1 to obtain the corresponding Z transform. So for this one, this is a Z transform and the corresponding ROC. For the second one, we apply the example 2 to get the corresponding Z transform and the ROC. And in order to have a global convergence, the final ROC should be the intersection of these two. So the Z, the magnitude of value of Z, the magnitude of Z must be less than 1 over B, greater than B. And the corresponding Z transform is given by their summation. So you can see that here, the ROC is a ring, corresponds to a ring in the 2D plane. And in particular, if the B has a value greater than 1, then this is an empty set. So in that case, we don't have any region of convergence. Now, when B is less than or equal to 1, we do have such a ring type ROC. Okay, so this shows that two-sided signals has a ring type ROC, ring shape ROC. And these more advanced ROC properties are also very, very similar to the properties of Laplace transform. And again, the only difference that here, always remember the shape of the ROCs looks like circle or ring. But the fundamental properties the logic are exactly the same. So let's look at this. So if the Z transform takes a rational form, then the ROC is always bounded by poles or extends to infinity in the Z plane. Which means if you have a poles if you find some poles of this Z transform, then the ROC should never contain these poles. Okay. So in this case, the only possibility is that let's consider simply. So the only possibility is that either the ROC extends outward the outermost pole. Outermost means that it is the pole with the largest magnitude. It's the farthest away from the original point. Okay. This is one region where the ROC will not contain any poles. The other possibility is that we consider this ring that goes through this pole. Then the second possible ROC is this ring between these two circles. So this region of ring is in between these two poles. So it will not contain any poles. And the third possibility is again the ring between, if I draw another circle around this innermost pole, the third possibility is the ring between these two circles. So the idea is exactly the same as the Laplace transform. The only difference is that here we draw the ROC in terms of circles or rings. Okay, so so here the ROC should not contain any poles. And moreover, if we for a rational Z transform, if the signal is right-sided, then the ROC corresponds to the region that extends outwards from the outermost pole. Because it is right-sided, so we know that the ROC is always outward. And you may have multiple poles, so the only way that the ROC will not contain any pole is that the ROC should extend outwards from the outermost pole. So in this case, the ROC should extend outward this biggest circle. And on the other hand, if the signal is left-sided and has a rational Z transform, then the ROC extends inward from the innermost pole. Right, so this is similar to the Laplace transform. Well, if we have a right-sided signal that has the rational Laplace transform, then the ROC is to the right of the rightmost pole. Okay. But here we are extending outwards. And this is an example where we are given a Z transform, but not specifying the ROC. So we can discuss different possibilities for ROC and their corresponding signals. So in this case, we first find out the pole of this Z transform. So the pole is defined as the root of the denominator. So the first pole is for this one is when Z equals to 3. And the second pole is when Z equals to 1/2. So you can draw them on the 2D plane. You have 1/2 and 3. So these are two poles. And then these two poles will divide the entire 2D plane into 3 ring-shaped regions. So what you do is basically, instead in Laplace transform, right, we always draw vertical lines as the boundary of ROC. But in the Z transform, we always draw circles, okay, as the boundary of ROC. So here we draw circles going through these poles. Another circle. And these two circles these two circles will divide the entire region into three smaller regions. Right? One is the inside the innermost hole, innermost circle. So this is the first possible ROC. And the second one is the rim between these two circles. This is the second ROC, second possible ROC. The last possibility is that outside the outermost circle. Right, so there are three different possibilities. And for different ROCs, later we will see that we can find different inverse signals. Yeah, and then once we know the basic properties of the ROCs, we can start to talk about the inverse Z transform. Again, here we'll basically leverage some existing pairs of Z transforms to help us identify the inverse. And you can see that if we are given such a Z transform with such an ROC, so this ROC is outward toward a circle, then the corresponding signal is a right-sided signal. Otherwise, if the ROC is inward to, inside a circle, then the corresponding signal is a left-sided signal. So based on once we specify the ROCs, we can use these existing pairs to identify the corresponding signal. So this part is the same as what we did in the Laplace transform. For example, here we are given this Z transform with specific ROC. So we want to find out the corresponding inverse. So the first thing we do is partial fraction expansion, and after that, you can find that this can be decomposed into these two simple fraction numbers. And then we are given from this overall region of convergence, we need to identify the region of convergence for each one of them. So in this case, here we have two poles corresponding to these two parts of the Z transform. So the first pole is Z equals to 4 here. The second one is when Z equals to 3. Okay, so these are the two poles. But the overall ROC is given as actually it should be 1/3 and 1/4. So 1/4, 1/3. So these are two poles, but the overall ROC is given by outward, the outermost pole. It's given by this one. And because this ROC is an intersection of the ROCs of these two Z transforms, so the only possibility is that for this one, the ROC is exactly the overall ROC. So outward this 1/3 circle. And for this one, the ROC is also outward, but outward the 1/4 circle. So therefore, we can infer that the ROC1 is Z, the magnitude of Z bigger than 1/4. ROC2 is the magnitude of Z bigger than one third. And then if you take their intersection, the overall ROC is simply this one. And now once you have identified the corresponding ROCs of these two Z transforms, you can go back to this table, figure out the inverse. Okay, so you use that table, you can easily find out the inverse, which takes this form. So in this case, both ROCs are outward to a circle. So that means their inverse corresponds to right-sided signals. And indeed, you find these two right-sided signals. Okay, we have a question. Is the Z transform generalized to TTFT? Yes. We have mentioned this at the beginning. So Z transform is so this is a general Z transform, right? Z is as a general complex number. We can write it as R times E J omega. So this is a polar form. And the DTFT is simply when R equals to 1. So basically, DTFT corresponds to Z transform on the unit circle in the 2D complex plane. So this corresponds to a unit circle on the 2D plane. Okay, so this is how we find the inverse. So the idea is exactly the same as the Laplace transform. Again, the difference is that here all the ROCs are ring shaped. Yeah, this is another example which I think I can kind of skip it. So this is basically, sometimes we can directly find out the signal by comparing with the power, by comparing the Z transform with the power series. So for example, let's say we are given this Z transform with such an ROC. We want to find out the inverse. Because the Z transform is given in a power series form. Like this is the second order term, Z to the power of 2. This is Z to the power of 0, and this one is Z to the power of -1. So this already fits into the definition of Z transform. So we just compare this with the definition of Z transform. Right, so we can see that, for example, here we have Z to the power of 2. So that means when n equals to -2, when n equals to -2, we have Z to the power of 2. And at that time, the corresponding coefficient is x -2. And from this equation, we know that the corresponding coefficient is given by 4. So we can derive x -2 is 4. Okay. So when n equals to -2, we have 4. And then we can, for each of these terms, we can, following the same logic, we can infer that, like here, this corresponds to when n equals to 0, so that we don't have this Z term. And the corresponding coefficient is 2. And this one corresponds to when n equals to 1. And the corresponding coefficient x1 would be 3. And all the other terms are zero because we do not have all the other terms. We only have three terms in this power series. So this is the signal that we find by, by directly comparing with the definition. And I think this part I can skip it. So the idea is that sometimes if the Z transform is given in this form, then we can find the signal by dividing, let me see, by simply dividing NZ with DZ and match terms with orders. Okay, again, the idea is to trying to express the given Z transform into this power series, and then you just compare their coefficients one by one. But we don't use this quite often in the homeworks. So I'll skip it. And then we can directly jump to all the important properties of Z transform. And most of them are the same as the Laplace transform. Okay, we have linearity. This is all the transform that we introduce in this course have linearity. And the corresponding ROC is their intersection at least. And we have time shifting, right? With a shift in time will cause a kind of a phase change in the Z domain. So basically, a time shift will lead to Z to the power of an additional factor of Z to the power of negative n in the Z domain. Okay, this is starting from Fourier transform. We have this type of property. And shifting in the Z domain. Okay, so this one is a little bit different. Because here is a discrete case, so the Z domain shift is actually given by XZ divided by Z naught. In the Laplace transform, we do not do division. So here is XZ divided by Z naught. This will, going back to the time domain, this will create an additional modulation signal, which is Z naught to the power of n times your original signal. Yeah, in fact, this is more like a scaling in the Z domain. And conjugation, the conjugation is a little bit different. So if we look at the conjugate of a signal, the corresponding Z transform is X conjugate Z conjugate. So there are two conjugates here. And in particular, if the signal is real valued, then the original Z transform equals to this double conjugated Z transform. Because when X is real, these two are equal, basically. And then this is the most important convolution property, right? Convolution in the time domain, in the discrete time domain, becomes multiplication in the Z domain. So in this case, we can apply Z transform to analyze discrete time LTS systems. And here we have the the differentiation in the Z domain property. If you take a derivative in the Z domain and multiply it by negative Z, this corresponds to n times xn in the time domain. So these are very similar to the Laplace transform, Fourier transform. And this is a initial value theorem similar to the Laplace transform. So if the signal is causal, then the initial value is the limit of the Z transform. Okay, and we can quickly look at some examples to how to apply these properties to calculate the Z transform. So here we want to find the inverse of this Laplace transform. So the Z transform. The Z transform is given by this log form, while the region of convergence is given by this region. So because of the logarithm, it is not clear how to take the inverse. We never see this logarithm in the table. So here we should consider relating it to the basic properties of the Z transform. So in the table, we are familiar with Z transform in the form of fractions, right? Like this one. So the only way to relate logarithm to fraction numbers is consider taking derivative of the log function, log signal, right? Because log x taking derivative is 1 over x. So this motivates us to think about the differentiation property. So therefore, we want to take derivatives in the Z domain. And by the differentiation property, such a derivative in the Z domain is related to the signal n times xn. Therefore, applying this property, we know that n times xn has this Z transform. Okay, so you plug in xz here, taking the derivative multiplied by z, you get this one. Therefore, by leveraging the differentiation property, we derived the Z transform of this n times xn signal. And then the rest of the steps, we still have 2 steps. Step 1, we need to figure out what is the signal corresponding to this Z transform. Once we have that, we just divide it because this signal corresponds to n times xn. So we just divide it by n to get the original signal xn. And in order to find the inverse of this signal, we can see that this Z transform is slightly different from the Z transforms that are given in the table. In the table, we are given such a pair of Z transform. And the only difference is that in the numerator, we have this additional term, a times c to the power of -1. And such a term, we know that it can be introduced by leveraging time shifting property. So that motivates us to apply time shifting to introduce this term. So basically, given this pair of Z transform, we shift the signal to the right by 1, so that by the time shifting property, the corresponding Z transform is given by this one. Okay, so therefore, you can find out the inverse signal of this Z transform. It's basically this one multiplied by a, and then in the end you need to divide it by n. So that's what you get in the end. Okay, so this one is a combination of differentiation in the Z domain and the time shifting property. And similar to the Laplace transform, we can also use Z transform to understand all the system properties of LTI, discrete time LTI systems. So for example, if when talking about causality, here causality means the ROC of the Z transform, of the corresponding Z transform, is the exterior of a circle and includes infinity. Why? Because by definition, causality means that the system impulse response is a right-sided signal. And we know for right-sided signals, the Z transform, the corresponding ROC of the Z transform should be extending outward. Okay, so this criterion can be used to characterize the causality of the system. And in particular, when the system frequency response Hz has a rational form, then causality is equivalent to the following two conditions. Now, first of all, the ROC should be extending outward to a circle, because causal means the Hn is right-sided. The signal response, system response, is right-sided. And the second criterion is that the order of the numerator should be smaller or should not be greater than the order of denominator. This is to guarantee that the ROC includes infinity. So infinity is a zero of this Z transform. So in that case, ROC includes infinity. So for example, for this LTI system, it is not causal because we can see that the infinity is a pole of the system. Therefore, the ROC does not include infinity. In that sense, it is not causal. It's not causal. And on the other hand, for this one, looking at the ROC, it is extending outward. So it satisfies criterion 1, and also it includes infinity. So it satisfies criterion 2. And in this sense, this is a causal LTI system. And stability is very similar to the Laplace transform. So in the Laplace transform, stability means that the ROC should include the y-axis. But here, stability means that the ROC should include the unit circle. And for example, given such a Z transform, we have two poles. One is 1/2, one is 2. Now, these two poles divide the entire Z plane into 3 regions. So there are 3 possible ROCs. And only one of them corresponds to a stable system. This one, because only this one includes the unit circle. The other two does not include the unit circle. Okay, so this is the stability. And including the unit circle implies that the system, the impulse response is absolutely summable. So that is a sufficient condition for stability. And then again, we can put these two things together. We can talk about causal and stable systems. And in this case, in order for a system to be causal and stable, we need to satisfy that all the poles must be within the unit circle. Okay. In the Laplace transform, in order to have causal and stable system, we must have all the poles must be lying to the left of the y-axis. Here, all the poles should lie within the unit circle. So for example, we can look at example 2. Now suppose the following system is a causal system. So we should discuss so let's discuss the stability of this system. Now, first of all, we can identify that this system has two poles. One is r to the power of e j theta. The other is r to the power of e negative j theta. So these 2 points are located on the circle with radius r, but with different phases. And because the system is causal, so the ROC should extend outwards. So therefore, we can know that the ROC is outside this circle with radius r. Because the 2 poles are located on this circle, somewhere on this circle, and then the system is given as a causal system, so the ROC is extending outward, and the only possibility is extending outside this circle, so that it will not include any poles. Okay, so then we know the ROC is given by this outward region. And then there are 2 cases depending on the value of R. Now this R is given in the system frequency response. If this R is less than 1, has a magnitude less than 1, meaning that this outer region will contain the unit circle, right? Because it is less than 1, so 1 is beyond this R. In this case, the ROC includes the unit circle, so the system is a stable system. Otherwise, if this R is bigger than 1, then 1 should be inside this circle, so that the ROC will not contain the unit circle. And in that case, the system is not a stable system. Okay, so here the stability is related to the unit circle in the Z-plane. And the last part is the unilateral Z transform, and I think you kind of you already have an idea of this unilateral thing. So again, it's the same as the unilateral Laplace transform. Well, we modified the definition of Z transform a little bit. We only start from 0 instead of net infinity. Okay. So this means that this kind of transform is very compatible with causal signals or causal systems. So this can be, because of this, you can understand this unilateral Z transform as the Z transform applied to the original signal times right? So the will restrict the summation to be within 0 to infinity. And because of this definition, the ROC of the unilateral Z transform is always extending outwards, because it can be understood as the Z transform of such a signal. And this is a right-sided signal. And by the property, we know that right-sided signal has outward ROC. So ROC is extending outwards. So for example, if we look at this causal signal, because it's causal, we know that by definition, the unilateral and the bilateral Z transforms are the same. Okay. So therefore, we can just consider its bilateral Z transform. And from the previous discussion, we know that this signal has such a bilateral Z transform. And in this case, this is also the unilateral transform of this signal. But for these signals, the unilateral and bilateral transforms are not equal, because it is not a causal signal. And we have seen this type of tricks in the Laplace transform. So the way to calculate the Z transform of this one is to, now first of all, by the definition of a unilateral Z transform, this is the original definition, okay, where the summation starts from 0. But then, because now xn equals to an plus 1 times un plus 1. But this un plus 1 starts from -1, which is weaker than the lower limit of this summation. Okay. Starting from 0 is stronger than starting from -1. So in that case, we can ignore this part and only care about this exponential part. Okay, so because the lower limit already handles the un plus 1 part. And after that, this reduces to a standard summation of infinite series. So you work out this infinite summation and you can find out the corresponding unilateral Z transform and this corresponding ROC. So this part is to just apply the infinite summation series formula. And for the unilateral transform, the most important thing is that when you apply the properties of this transform, many of the properties is sensitive to the initial conditions of the signal. For example, convolution property only holds for causal signals because the unilateral transform are designed in a causal way. And then here we have this time shifting property, the time delay property. If the signal is delayed by 1, then the corresponding unilateral transform. Now this is kind of like the time shifting property. Okay? So this will give us a Z to the power of -1 factor in the Z domain, and as well as an additional term that depends on the initial value. This is not the initial value, but the value at this -1. Okay, and this is how we derive this. You can follow in the definition, and step by step you can derive it. So I will ignore this part. But the key is that when you apply unilateral transform to this time-shifted signals, you have to know this. You have to know these initial conditions. Okay, and these are the and in addition to this single time delay property, we have this time delay by 2. This is an additional property, time delay property. So if your signal is delayed by 2, then you basically you will apply the time delay property to this one more time, and you can have xn minus 2, the corresponding unilateral transform depends on these two initial conditions. And this is like a standard time shifting property in the Z domain, right? And these two terms correspond to the initial conditions that we need to know when we apply the unilateral transform. And this is a time advance property, where instead of n minus 1 or 2, we are looking at xn plus 1. And for this one, the corresponding Z transform is given by, again, this is a standard time shifting property with the second term depending on the initial value, initial conditions. Therefore, when we apply the unilateral transform to analyze difference equations in the discrete time domain, right? So in continuous time domain, we talk about differential equations. And in the discrete time domain, we talk about difference equations. Now, when we apply the unilateral transform to analyze difference equations, we need to consider these initial conditions. And we have this example, well, given a causal LTI system defined in terms of a difference equation, we want to solve this equation. So if we are given such an input discrete time signal and such an initial boundary condition of the output, we want to solve the corresponding output signal. So the idea, because we are given the initial conditions, so the idea is to apply the unilateral transform. And once you do that, yn becomes yz, right? And yn minus 1, you have to look at the difference time delay property for this one. So you have y negative 1 plus z inverse times yz. Okay, this is the unilateral transform of yn minus 1. And then you have on the right hand side, you have xz. Now y negative 1 is given as beta. This is given, and xz is alpha times un, and this signal we know is Z transform. Okay, so we can calculate this one. So once these two are given, we can go over the details the next time. But once these two are given, you can solve for the unilateral transform yz. Okay, it's something like a fraction number, and then from there you can identify the region of convergence, and with that you can find out the inverse. Okay. And similar to the unilateral Laplace transform, the region of convergence is clear because for the unilateral transform, the ROC is always extending outwards. So what you do is to find out all the poles of this Z transform and looking at the outermost pole. So the ROC would be extending outwards the outermost pole. Now with that ROC, you can come back and find the inverse of this Z transform by referring to the table. Okay, So let's stop here. So next time we can go over these last two examples as well as the review lecture. And if we do have questions or homeworks, please come to the office hour or send me an email. We can schedule an individual meeting. Okay, thanks guys. I will see you next Tuesday.
Thank you.